We were discussing about the problem of particle trapped in a one-dimensional box or the square well potential. Now solving the steady state Schrodinger equation, we found that the boundary condition leads to the quantization of energy. The energy eigenvalues En is equal to n square pi square h cut square divided by 2 m L square. L is the width of the box. Where n is equal to the quantum number 1, 2, 3, etc. Now we want to obtain the solution of the Schrodinger equation, that is the wave function. So the wave function psi n is given by a sine square root of 2m En by h cut times x. We have assumed the general solution a times sine function plus b times cosine function, but the one of the boundary conditions satisfied only if b is equal to 0. So we have discarded the cosine term and only sine term is exist. Now substituting for the value of En is equal to n square pi square h cut square divided by 2m L square. So 2m cancels, and if you take the square root, you will get n h cut cancels divided by L. So you get psi n is equal to a sine n pi x by L. These are the eigenfunctions of the system corresponding to these eigenvalues En. So psi n are the eigenfunctions corresponding to eigenvalue En. Now we can see that psi n is a well-behaved wave function, or it satisfies all the requirement for a well-behaved wave function that we discussed in our previous class. That is, it is finite, it is a sine function, so it is finite, single valued. Sine function we know it is single valued, and psi n and dou xi n by dou x are continuous. The derivative is cosine function, so it is also continuous. So it satisfies these conditions. And one more condition for well-behaved wave function is that its integral minus infinity plus infinity mod psi n square dx should be finite. So that is the condition came from the probability interpretation of wave function, that the total probability should be finite. Shorter probability of finding that particle from minus infinity to plus infinity, or the entire space, should be finite. So we can check that. So this is equal to mod psi n square is a square sine square of this function. A square is constant. So instead of integrating from minus infinity to plus infinity, we can integrate it from 0 to L, because we know this is x equal to 0 and L, psi is equal to 0 outside this potential barrier. So psi is equal to 0 before x equal to 0, and after x equal to L, psi is also 0. So psi is non-zero only between x equal to 0 and L. So instead of integrating from minus infinity to plus infinity, we can integrate from 0 to L. Now using this identity, sin square theta is equal to half 1 minus cos 2 theta. So integrating this first term, we will get x, half is taken outside, first term x, second term cosine, integral is sine function 0 to L. Now applying the limits, we will get upper limit L and lower limit is 0, and sine function sin 0 is 0 and sin 2 n pi is also 0. So there is no contribution from the sine term. So we can see minus infinity to plus infinity mod psi n square dx is a square by 2 L. So a is a constant, L is the length of the or width of the barrier. So we can see it is finite. So it satisfies all the conditions required for a well-behaved wave function. So the eigenfunctions that we obtained satisfy all the conditions for well-behaved wave function. Now we can think about the normalization. The normalization condition is given by minus infinity plus infinity mod psi n square dx is equal to 1. This is a condition for normalization. So normalization condition is required to easily interpret the probability from mod psi square. So I will explain. So by comparing this equation 6 and 7, so we have minus infinity plus infinity mod psi n square dx is equal to a square by 2 L, and the condition for normalizability is that must be equal to 1. So equating the right hand side of equation 6 and 7, we get we can fix a is equal to square root of 2 by L, or 1 is equal to a square L by 2, or a is equal to square root of 2 by L. Now substitute a in equation for wave function, that is equation 5. We get psi n is equal to square root of 2 by L sine n pi x by L, where n is equal to 1, 2, 3, etc. So this is the normalized wave function. So this is the unnormalized wave function. We can normalize using this normalization condition, and we obtain the normalized wave function. Now the wave function and probability density of a particle is represented in this picture. The first diagram shows the wave function for different quantum number n equal to 1, 2, etc. For n equal to 1, psi n. So if n equal to 1, this is pi x by L. So it will look like this. Now if n equal to 2 pi x by L, so it varies like this, and n equal to 3. Now the probability mod psi square, square of this, we will get mod psi 1 square like this, mod psi 2 square like this, 2 peaks, mod psi 3 square, we will get 3 peaks. Now we can make the following interesting observations from this graph. First thing is that psi n may be negative. So sine function here you can see it is negative, here also it is negative. But probability is always positive. We are taking the square of this, so the probability is always positive. That is essential to satisfy the probability condition. Probability cannot be negative. നമുക്ക് ഒരു 50% അല്ലെങ്കിൽ 30% എന്ന് പറഞ്ഞാൽ meaningful ആണ്. But അതല്ല, negative 5%, negative 30%, it is meaningless. So psi square or probability cannot be negative. So you can see it is satisfied. Second thing is that mod psi n square is equal to 0 at x equal to 0 and x equal to L. You can see mod psi n square is equal to 0 at x equal to, for any value of quantum number, for any quantum number, mod psi n square is equal to 0 at x equal to 0 and x equal to L. So that is the requirement from the boundary conditions. Psi should be 0 at the boundary. The infinite potential well ആണ്. അപ്പോൾ ബൗണ്ടറിക്കും ഇതിനപ്പുറത്തും psi wave function 0 ആവണം. Wave function 0 ആണ്, അല്ലെങ്കിൽ പ്രോബബിലിറ്റി 0 ആണ്. പ്രോബബിലിറ്റി 0 എന്ന് പറഞ്ഞാൽ അതിനവിടെ കാണാൻ സാധ്യതയില്ല. അതായത് ഇതിൻ്റെ വാൾസും ഇവിടെ നിന്ന് അങ്ങോട്ടും ഇൻഫിനിറ്റ് പൊട്ടൻഷ്യലാണ് ഇവിടെ നിന്ന്. ഇവിടെ ആ പർട്ടിക്കുലർ കാണാനുള്ള സാധ്യതയില്ല. So mod psi square is 0 at x equal to 0 and x equal to 0. That is automatically came from the boundary condition itself. Now for n equal to 1, the lowest energy quantum number, n is equal to 1, we can see the maximum probability of finding a particle. അതായത് E1 എനർജി ആയിട്ട് ഉള്ള ഒരു particle കാണാനുള്ള പ്രോബബിലിറ്റി എവിടെയാണ് കൂടുതൽ? At the middle. Middle means L by 2, at the middle of this box. So mod psi 1 square is maximum at L by 2, the middle of the box. അപ്പോൾ E1 എനർജി ഉള്ള ഒരു particle മാക്സിമം പ്രോബബിലിറ്റി അതിൻ്റെ സെൻറ്ററിലാണ്, ആ ബോക്സിൻ്റെ മിഡിലാണ്. But what about psi 2? E2 എനർജി ഉള്ളൊരു particle, അതിൻ്റെ പ്രോബബിലിറ്റി മിഡിലിൽ 0 ആണ്. So that is what quantum mechanics says. But classically, classical physics suggests same probability everywhere. ഒരു particular നമ്മളൊരു ഈ ക്ലാസ് റൂമിൽ ഒരു ഇലക്ട്രോൺ വെച്ചിട്ടുണ്ടെങ്കിൽ ആ ഇലക്ട്രോൺ എവിടെ വേണമെങ്കിലും ആവാം. ഈക്വൽ പ്രോബബിലിറ്റിയാണ് എല്ലായിടത്തും ക്ലാസിക്കൽ ഫിസിക്സ് പറയുന്നത്. പക്ഷേ ക്വാണ്ടം ഫിസിക്സ് അത് E1 എനർജി ആണെങ്കിൽ അതിൻ്റെ മിഡിലായിരിക്കും അതിന് മാക്സിമം വരുന്നത്. E2 ആണെങ്കിൽ അതിൻ്റെ മിഡിലിൽ 0 ആയിരിക്കും, വേറെ 2 പൊസിഷനിലാണ് മാക്സിമം വരുന്നത്. E3 ആണെങ്കിൽ വേറെ 3 പൊസിഷനിലാണ്. ഡിപ്പെൻഡിങ് ഓൺ ദി എനർജി അതിൻ്റെ പ്രോബബിലിറ്റി മാറുന്നു. സോ ക്വാണ്ടം പ്രോപ്പർട്ടീസ് കമ്മിങ് ഹിയർ. Now you can see 2 examples worked out in your text and other pieces. Example 5.4 and 5.5 in other solved problems in other pieces, and in your text it is problem 2 and 3 in page number 136 that we already discussed at the time of expectation value of position.